Greetings, geometry students. Today we're going to be looking at a very important theorem that once again does apply to all types of triangles that you will ever see, and that is the triangle inequality theorem. Please copy down the title. The date for these notes will be Friday, December the 5th, and please copy down your objectives. Our stated objective for today is to learn the applications of the triangle inequality theorem. Now, I imagine this is probably going to be a rule that you have never seen before. It is not particularly difficult, but it is a little procedure that we're going to need to become familiar with. On our assignment, you're going to demonstrate the ability to apply the triangle inequality theorem in order to determine whether provided lengths can form a triangle, and also to determine restrictions for unknown third side of a triangle. Got a little bit of a grammar issue in that paragraph. I apologize for that. And your essential question for the day is, can I use the triangle inequality theorem to solve the provided problems? As always, anytime you need more time to get something copied down, press pause on the video and then press play when you're ready to move on. Do not allow the video to just run past you even though you haven't finished a particular slide up. Okay, so let's get started. All right, let's jump right to it. The triangle inequality theorem. Now, the triangle inequality theorem says that any two sides of a triangle must be able to add together to be longer than the length of the third side of the triangle. Again, any two sides of a triangle must add together to be longer than the length of the third side of the triangle. Now, typically, this only causes problems in one particular location, and that would be the two smallest sides of the triangle trying to add together to be larger than the length of the third side of the triangle. However, we're not going to isolate ourselves simply to that one calculation. We are going to go ahead and do all three because there is a different application to this rule, as you will see toward the end of this lesson, and you will need to be able to do all three calculations. Anyway, let's take a look at what this looks like in a diagram. Here is a typical triangle. It has side lengths of A, B, and C. Now, the triangle inequality theorem says any two side lengths of a triangle must add together to be larger than the length of the third side of the triangle. So one possible application of that would state that the side length A must be able to add together with side length B to be larger than the side length C. But as you've probably already guessed, that's not the only way that these three side lengths can be added up. Another possibility would be that B must add together with C in order to be larger than A. And also, C plus A must add together to be larger than B. Now, three sets of sides on a triangle basically dictates that there will be three inequalities that will need to be considered. A plus B adding together, B plus C adding together, and C plus A adding together to be larger than whatever the remaining side length was. If any one of these inequalities turns out to fail, then the entire theorem is false, meaning you do not have a triangle. Okay, so let's look at the background behind this. It's actually a pretty simple explanation, especially when you look at it graphically. Okay, so let's assume for a moment that it might be possible for two sides of a triangle to add together and still be smaller than the third side of the triangle. I mean, after all, what can it really hurt if these two side lengths simply add up and don't reach the length of the third side? Let's take a peek. Let's say we have a triangle that has side lengths of 4 and 5 and 10. Now, if a triangle has side lengths of 4 and 5 and 10, and the triangle inequality theorem tells us that in all instances, any two side lengths must add together to be larger than the length of the third side. That would mean that 4 plus 5 would have to add together to be larger than the remaining side length, which is a 10. The triangle inequality theorem says that that means this is not a real triangle. Well, what's the big deal? Let's take a look at a diagram of that. Now these three side lengths are actually drawn to scale. So in this little computer program, I have measured out a line segment that is 10 units and a line segment that's 5 units and a line segment that is 4 units. Connected them at as many vertices as possible, and you can right off the bat see the problem. There is not enough length left over for the blue side, the 5, and the green side, the 4, to actually enclose the figure. So this is not a triangle. In fact, it's not a polygon of any kind. We don't have a definition for polygons yet, but polygons have to be enclosed figures. Clearly, this one is not enclosed. Okay, so let's look at a real example. Is it possible for the following lengths to form a triangle? And our lengths are provided for us as 3, 4, and 5. Okay, now you don't have to write this sentence down again because you've already got it written down. Any two sides must add together to be larger than the length of the third side. Okay, so let's do copy down the math here. Triangle inequality theorem tells us all of the following three statements must be true. 3 plus 4 must add together to be larger than 5. 4 plus 5 must add together to be larger than 3. 5 plus 3 must add together to be larger than 4. These are the three different possible combinations of any two sides of this triangle adding together to be larger than the length of the third side. Let's look at the math. On the first equation, 3 plus 4 is obviously 7. 7 is greater than 5. That is a true statement. That's good. Triangle inequality theorem likes true statements. In the center, 4 plus 5 is 9. Is 9 greater than 3? Of course it is. That is also a true statement. On the right-hand side, 5 plus 3 is 8. Is 8 greater than 4? Yes, it is. So we have true statements in all three of these cases. This means the triangle inequality theorem does like these measurements, so yes, these lengths can form a triangle. Let's look at another one. Is it possible for the following lengths to form a triangle? We have 9, we have 12, we have 2. Okay, so by the triangle inequality theorem, all of the following three statements must be true. Any two side lengths must add together to be larger than the length of the third side. So the inequalities would be 9 plus 12 would want to add together to be larger than 2. 12 plus 2 would want to add together to be larger than 9. 2 plus 9 would want to add together to be larger than 12. Okay, on the left side, 9 plus 12 is 21, and 21 is most definitely larger than 2. That is a true statement. In the center, 12 plus 2 would add together to be 14. 14 is certainly larger than 9. That is a true statement. On the right side, 2 plus 9 would add together to be 11. We have an error here. 11 is greater than 12 is what the statement currently says. The triangle inequality theorem wants 11 to be greater than 12. The problem is it is not greater than 12. So we have run into a false statement. If you run into any one false statement while examining the triangle inequality theorem, then the entire problem is incorrect, and you would be forced to say, no, these lengths cannot form a triangle. The 2 and the 9 are not long enough to reach the ends of the side that is 12 units long. Now I think you get the idea here, but there's another situation that we need to examine. Is it possible for the following lengths to form a triangle? And the lengths provided are 11, 5, and 6. Okay, so obviously 11 plus 5 would need to add together to be larger than 6. 5 plus 6 would need to add together to be larger than 11. 6 plus 11 would need to add together to be larger than 5. On the left side, 11 and 5 is 16. 16 is certainly greater than 6, so we are good so far. In the center, 5 plus 6 is 11. The statement now says 11 is greater than 11. Now, it is a tie, but the problem here is we don't have a tie goes to the runner rule or anything like that. 11 is not greater than 11. It's very, very close, but it is inaccurate. So we have a false statement. There is no sense in going any further in the problem. These lengths cannot form a triangle. All right. Now, there is a different manner in which the theorem can be used in. Okay, and you will find that as we travel through geometry. We will find that there are often more than one way to use the rules that we come up with. Okay, so the other side of this theorem is that it can be used to determine possible or potential boundaries for the lengths of an unknown side of a triangle. Okay. For example, let's say a triangle has side lengths of 5 and 7, and then we are left to determine what is possible, what do you know about the length of the third side of the triangle. Now, some people will foolishly say that it's got to be a 6 because it's got there's a 5 and a 7, so obviously there's a number 6 missing in between those, and that's a silly reason. Okay, there's got to be more to it than just simply the sides are counting in numerical fashion. Okay, let's take a look. The rule for the triangle inequality theorem still holds true. Any two side lengths must add together to be larger than the length of the third side. That is going to provide us with a fair amount of restrictions on what this side length can actually do. Okay. But looking at the inequalities, 5 plus 7 must add together to be larger than whatever the third side length is. We'll simply call it x. Also, 7 plus the unknown third side x must add together to be larger than 5. And also, the unknown third side x must add together to be larger than 7. These are the three inequalities that we have set up for the last three examples. The only difference is, right now, one of these sides is unknown. However, all we're going to do is we're going to solve these equations much the same as we were solving the other ones just a moment ago. On the left side, 5 plus 7 is 12. We have a statement that 12 is going to be greater than the value of x. Okay, so that is a restriction. Our side length must be smaller than 12. In the middle, we have to actually solve for x. We need x to be by itself. So that positive 7 that's on the left side of x does not need to be there. So we're going to move that positive 7 by subtracting it to the other side of the problem. So we're going to subtract 7 from both sides. That will give us x is greater than negative 2. Okay, so that is saying that our side length must be larger than the value negative 2. On the right side, we have a similar problem to what we had in the middle. X is not by itself, so we're going to get it by itself. That plus 5 does not need to be there, so we will move it by subtracting it to the other side of the problem. And by doing that, we have 7 minus 5 on the right side of the problem, and that is 2. So the statement says x is greater than 2. So our unknown side length x must be larger than the value of 2. Okay, now let's look at what these three inequalities actually mean to the problem. First off, hopefully you notice something went wrong in the middle of there. we had a negative side length show up in our triangle. X was greater than -2. Well, there is no such thing as a negative side length in a polygon. So on these problems, you are going to get one that is going to turn out being a negative value. You will disregard that inequality and instead pay attention to the other two. Okay, so our two inequalities are that x is smaller than 12 and x is larger than 2. One of the easiest ways to get a grip on this information is to place the results of those inequalities onto a number line. We only need two particular locations on this number line, and it really doesn't matter where they are. I just put one on one side and one on the other. And I'm going to allow these locations to be 2 and 12. So I'll start off with the 2. Obviously 2 is the smaller of the two values, so it's going to be off to the left side. And the inequality dealing with 2 says that x must be larger than 2. So 2 is not a possibility, but the possibilities are that it is larger than the value 2. So I'm shading towards the bigger numbers away from 2. 12 is the other value that is going to be on our number line, and the inequality says that x must be smaller than 12. So 12 is not a possibility, so it gets an open circle as well, but the values that are smaller are definitely possible. So I shade towards the smaller numbers, or the left side of the number line. Where we are interested in the answer is where these two shading areas are going to overlap each other. So obviously they are completely overlapping each other in between the values of 2 and 12. So x must be somewhere between 2 and 12. That is our answer. So you record your answer in what we call the sandwich notation for inequalities. 2 is smaller than x, which is smaller than 12. Okay, let's look at another one, see if we got the grip on that. If a triangle has side lengths of x and 7 and 15, what do you know about x? Well, once again, all the three following inequalities must be true. X must add together to be with 7 to be larger than 15. 7 must add together with 15 to be larger than x. And 15 must add together with x to be larger than 7. Okay, so solving the first equation, let's subtract the 7 away from the x, and that will give us a statement of x is larger than 8. In the center, 7 and 15 will add together to be 22. 22 must be larger than x. On the right equation, we're going to move the 15 away from the x. Subtracting it to the other side, we have a statement of x is greater than -8. And again, we will disregard this inequality because there's no such thing as a negative side length. Okay, so on our number line, we have 8 as the lower side, and x must be bigger than 8. On the larger side, we have 22, and the inequality says that x must be smaller than 22. So clearly x is going to be in this area between these two values. So in sandwich notation, that is x is less than, or 8 is less than x, which is less than 22. Those are the boundaries for the third side length. Okay, last example. This one's going to be on you. A triangle has side lengths of 5 and 5 and x. What do you know about the length of the third side? I want you to set up the three inequalities. I want you to solve the three inequalities. I want you to graph the two inequalities that are the result from the triangle inequality theorem, and provide an answer in the sandwich notation, just like the last two examples have done before this one. Record your summary, jot down any questions that you may have, and always keep your essential question in mind. Can I use the triangle inequality theorem to solve the provided problems? I appreciate you finding time to get your notes taken care of, and I'll see you in class.